Alright, we're going to continue our discussion about functions. This is a new type of function. It's called piecewise function. And what is a piecewise function? A piecewise function is a function that is built by using pieces of other functions on different intervals. So what that means is, if I've got this graph here, I'm just going to be very arbitrary here. Let's just say I break it up into these different intervals. In the blue interval, I might have maybe that line right there. In the green interval, we might have maybe that parabola. And in the yellow interval, maybe we have that line. And we see that these are three different functions. It still all passes the vertical line test, but this is a piece of a line. This here would be a piece of maybe a parabola, and here's a piece of another different line than what we started with. Okay, so the way that we describe that is we're going to say f of x, our function, and we'll say it is equal to, and then we'll put this big curly brace. Okay, and it'll be right here, we'll have function number 1. And let's actually, yeah, all right, it's function number 1. You might hear me call it a rule. Here would be function number 2. And here would be function number 3. Now we can write as many as we want. It can be 2, 3, 4, 5. But then we put a semicolon in those spots, or a comma. And then it will be the interval. And there's different ways we'll express the interval for each of these. We can do it in set builder notation, or we might be able to do it in just interval notation. And it's going to be the interval that we saw that blue one. Okay. Then here we have the interval that we saw that green one in, and then here we would see the interval that we see that yellow one in. Okay. So I'll teach you in this video how we look at a rule and evaluate a rule. Okay, so we look at this piecewise function. How am I going to evaluate -2, 3, and 1? We'll do those couple examples, and then we'll take a couple examples and we'll graph them. Okay, and talk about how we can come up with our piecewise function image. All right, so this is how do we evaluate piecewise functions? Well, the first thing we're going to do is we're going to ask ourselves, what are we evaluating? Okay, so -2 is the input. So I need to look at my rule here and say, okay, where does -2 fall? Does -2 fall in that interval, or does it fall in that blue interval? Okay, well, -2, is that greater than or equal to 1, or is it less than 1? It's less than 1. So that tells me then I'm going to plug -2 into that rule right there. So f of -2, plug it in here. So -2 squared will give me 4. Now I'm going to go to the next one. I'll get 3. And I ask myself, okay, where does 3 show up? Is it in the green interval, or is it in the blue one? It's in the green one. So I'll plug 3 in. So it'll be -3 plus 2 gives me then -1. And then f of 1. So where does 1 fall? Okay, you just got to pay attention to your symbols here. They both have 1, but this one says I'm getting to 0.99999. I can't really input 1. This one says I put 1 in. So put 1 in there, and I get 1 back. So if I'm asked to evaluate a piecewise function, I first have to determine what interval is that value, that input falling in, and that then is going to tell me which rule to plug into. If we were to graph this, let me see if I can cut and paste an x and y axes in here pretty quick. Okay, so the way that we graph a piecewise function is to first look at, I just go top rule down. Okay, so I'm going to start with the top one. And it basically says, okay, for values of x being greater than 1, greater than or equal to 1, I'm going to apply this rule. So what I'm going to do, because I know this is a linear line, okay, so that's one thing to know is what kind of function you have here. I'm going to go to that point right there, whether it's included or not. I'm always going to use that number right there. I'm just going to plug it because it's a line I can plug in, makes things easy. So I'm going to go to x being 1, okay, and if I plug in x being 1, I should get 1 back. So I know right there I'm going to have a solid dot. Okay, now, because I know it's linear, so that's my first point. Now I know it's linear. I know that point is on my line. I've got my slope here, down 1 over 1. I can get that point there. And that's really enough to get what I need here for that first rule. But if you weren't certain about how we do that slope, choose a number that is bigger than 1. Choose like a number like 5. Plug it in here. -5 plus 2 give me -3. So I'm at 5. I'm down at -3. Okay. Oh, missed it. -3. And now all we're going to do is, because to the right of 1, this green interval is telling me that you keep going on forever. So what I'm going to do is I'm going to take from this point here, I'm going to graph over here. And that tells me right now that red line is -x plus 2. And you can see that's only being graphed for x values that are greater or equal to 1. Now we go to the next rule. The next rule says for values that are less than 1, you're going to go to x squared. Well, even though it says less than 1, I'm still going to graph at 1. Except for now on this graph, it's going to be an open dot. So if I'm looking at x squared on an x value of 1, the y value would be 1. But it's going to be an open dot right there. Okay. Now, overall, because it was on top of a closed dot, when I use my vertical line test, it will be a closed dot. But now, I think about what does my graph look for like x squared less than that? Well, 0, 0 is a point. -1, 1 is a point. -2, 4 is a point. So we know these from our parent function. And then we'll just connect that with a smooth curve. And because it goes on, it's less than, it doesn't have a endpoint, so it's telling us that we're going on to negative infinity. Put an arrow on there, and that's what our function looks like. Okay, that was open on the blue, closed on the red, so overall it is a closed dot. Okay, but it evaluates in our rule only for this red, or for this green one. This next one here says g of x. Okay, so in this case, it's saying x is less than -5. We've got -2 as our rule if x is between -4 and 0, including 0, and root x if x is positive. So we go g of -7. So I got to figure out which one of these intervals does -7 belong to. -7 belongs to this interval, this yellow interval. So I'm going to plug in -7. And that's going to give me, so -7 plus 1 is -6. Absolute value is 6. Next one is 16. So figure out where is 16. 16 is in this green one. So plug in 16 to that. I get 4 back. -1. Find where -1 is. -1 should be in this interval here. Now my rule is a constant linear function. So it just spits back to -2. -4.5. -4.5. Now think about this. This is everything less than -5, and this is -4 up to 0. -4.5 is in the gap between that number there and that number there. -4.5 is not defined for in this. It's undefined. There's no rule here that incorporates -4.5 as an x value. Try 0. Okay, so 0, it's a debate whether it should be the blue or the green one, but because the blue one has equality and the green one does not, we plug it into the blue one and we get -2 back. Take some time to graph this one. Alright. So what I'm going to do, I'm going to come over here. First one here, absolute value of x plus 1 for x is less than -5. So I'm going to go -5 first. Even though it's not equality, that is kind of my cutoff value. And I'm either making an open dot or closed dot based off the symbol. So I'm going to go to -5 and say, okay, if I plug -5 in here plus 1, and then take the absolute value of that, that should put me at 4. So at -5, I'm up at 4. And like I said, because it's less than, I'm going to make a open dot. Okay? Now I'm going to go to the left of that. Okay, so let's try -6. If I plug -6 in, plus 1, I'm going to get absolute value of -5, which is just 5. So we get that. And my graph, if I keep trying those over here, is going to look like that. Now, you can do it this way as well. If you know what x plus 1 looks like as an absolute value, and hopefully we do, we know it should look like that. That's the entire thing. Okay, that's if I just said graph f of x equals absolute value of x plus 1. That's what you would come up with. But if I said graph it just for values to the left of -5, you would then take this stuff here and you would erase it. And that's what you got. Absolute value of x plus 1 to the left of -5. Now we're going to go between -4 and 0. -4 to 0 is a height of -2. So this is basically saying at -4, we should be at a height of -2. Now, -4, that symbol right there is just less than. It's not equal to. So I'm going to put an open dot. And then at 0, we're equal to, so I'll put a closed dot. And because I know this is linear, it's constant, that's what that line right there is going to be. And then the last one, okay, I'm going to do some blue. Choose this point first. So you see that I'm choosing, when I'm graphing these, the first point always chooses these endpoints. This one was, I chose that endpoint of -4, and because it's a between statement, I also choose that endpoint there. Okay. Here I go to this endpoint, 0, plug it in here. 0, 0 gives me, or x being 0 plugs in, gives me 0 here. Square root of 0, 0. So I get a point right here at 0, 0. Now it's open dot there because I do not have equality here. Now I'm going to choose values that are bigger than 0. Well, I'm going to take square root, so I'm going to try numbers that I like. Taking square roots of, like 1, like 4, 9, and we'll graph that to the right. So now we have our piecewise function. It's piecewise because it's a bunch of pieces. It's a function because if I put in my vertical line, does my vertical line always just intersect one time? Intersecting that black stuff just once. Intersecting the red stuff here just once. Now there is a question there, right there. How many times do I intersect right there? But let's remember, this was a closed dot there. That's an open dot. So that open dot really means like 0.000000, how many times I can say that, and then 1, and not 0. So this blue line is just, this solid blue line is just coming up to this highlighter line and not touching it. It's just coming right up close to it. So we pass there, and we should pass then everywhere over here as well. Okay. Notice there was a region. There was a region in which there was no points being graphed. That region right there, nowhere in the Cartesian plane is there a point being plotted in that yellow rectangle. Well, that's the values between -5 and -4, and that is why this one here is undefined. There is no y value for any x of -4.5 or any x that's in that region for that matter, so it's undefined. Do another one here. This one is a unique one because, I don't want to say unique, but it says there's a very important one. Important piecewise function. It says for every value that x is greater than or equal to 0, you're going to graph the line y equals x. So I'm going to go to 0. It's going to be the first point. Plug in here, I get a 0 back. Close dot, because it was equal. Now numbers to the right, I can keep plugging things in, or I can know that this, like I said in the past, this is linear. So I can go up 1 over 1. And keep getting that. And I can connect those. Okay. Now over here it says if x is less than 0, you get negative x. So I'll plug 0 in. Always choose my endpoints. Plug 0 in here, you get -0, which is 0. And I'll put an open dot at 0, 0. Well, it's a closed dot on top of an open dot, or an open dot on top of a closed one, how you want to view it. So it closes it effectively. Now I'm going to try, since this is linear, okay, my slope is rise over run, so it'd be -1 over 1. Okay, so the way I'm going to do that, I'm going to go up 1, left 1. That would give me a -1 slope. Up 1, left 1, -1 slope. Okay, or if you wanted to plug in like x to be -2, I plug in x to be -2, I get the opposite of -2, which would just be +2. So I get this. Okay, and that should look familiar. That is the absolute value function. So what we have here is if the absolute value of f of x is what we're looking for, then it is written as the piecewise function, or it is defined as the piecewise function. When x is greater than 0, you have just x. When x is less than 0, you have -x. I wrote it this way. I'm just kind of familiar with GeoGebra. It's just in my mind right now. Most times we write the rule first and then the inequality or the interval. GeoGebra is kind of backwards. I think you have to write if x is greater than or equal to 0, then what it should look like. So I'll kind of demonstrate this in GeoGebra. Control, I'll get out of here. Go back to standard. All right, so if I go if, so when I put parentheses here, so if, it should, there you go, you see it says condition. So the condition is the interval. So let's just say if, I'm doing one of those other ones. Let's do, what do we have? The absolute value of, so let's graph this one here to see if that models what we came up with. So let's say if x is less than -5, graph the absolute value of x plus 1. And I believe then you have to do what's called nesting here. So I'm going to actually hit comma and write another if statement. So if, and that gives me a condition. So now I'm going to go -4 is less than x is less than or equal to 0. Then we'll tell it to graph -2. And then I think I need to put a comma here and go if again, and x is greater than 0, comma, square root of x, and then we'll just make sure we got enough parentheses here. That should be it. Hit enter, and you see then how it types that in. It's kind of messy, but you can see that our graph that we wrote by hand, similar to what we get here. The only thing that GeoGebra doesn't do for us is at this juncture right here, I'm not sure which one is open and closed. That's kind of a pitfall of this. But I can evaluate this now. I can say, you know, what is f of 0? Give me back -2. So it reminds me of f of 0. Well, it has to be, it's filled in here, and it must be open there. That's kind of how you do that in GeoGebra. The way you type it in is kind of backwards in the way you would normally write it. So coming back down here, maybe we should say the absolute value of f of x is equal to f of x, the piecewise function of x when x is greater than or equal to 0, and negative x when x is less than 0. And just depending on the textbook that you're in, that one might be the greater than one, and that one might be less than or equal to. So the equality part can show up in either one of those, doesn't matter, for defining the absolute value function. This example, same idea. So I'm going to remind myself that this is linear, so is this one. So I've got some linear graphing tools at my disposal that we know from the past. I'm going to go to -1, so x is -1. Okay. Now, because I don't know my y-intercept when x, because I'm not looking at the entire graph anymore, so I'm not going to use my y-intercept in my y equals mx plus b graphing tool. I'm going to use just straight substitution. You guys have done this, create an x and y chart. I'm going to choose -1. Plug that in here, so we get -2 minus 1 is -3. So at -1, I'm down at -3. Now I'm going to put an open dot. Okay. Now my slope is 2, and I'm going to be graphing to the left. So I need to go a rise of down to left 1, down to left 1, and that will be what we're looking for. That's that first rule, 2x minus 1. Now, like I said, I'm not using my y-intercept, but if you wanted to, you could. You just gotta be, you're gonna be erasing things. So you could say, okay, I'm going to -1, my y-intercept, and then apply my slope up 2 to the right 1, and then say, okay, well, I'm going to graph that whole thing. So you do this thing, and then say, okay, well, what values of x am I keeping? Well, I'm going to keep x being less than -1. So I'm going to basically do kind of this game here, and these are all my values less than -1. So I would keep that stuff, and I would take my eraser and erase all this other stuff, which effectively then would leave me with just that there graphed in black. Now, for x being greater than or equal to 1, x is greater than or equal to 1 from here. Okay, so that's the x value. So now I should be at a height of 3. That's going to be a closed dot because of the equality. And then if I'm to the right of 1, it's still at a height of 3. Okay. So what we see here is, and we saw it in one of the previous ones, is there's a jump here. There's a gap. Okay. This is still functions. Functions can have gaps, but this is what we refer to as a discontinuous function, or Usually that's an adjective to determine the flow of the curve. Okay, continuous means I can graph the whole thing without lifting my pencil. Think about this: can you graph this entire absolute value without lifting your pencil? And you can, so that would be continuous. This one, you have to lift your pencil to go from left to graph this black one, lift my pencil to come down here and get this red one, lift my pencil to come up and get this blue one. So that is discontinuous. Still a function, but discontinuous. Okay? And we'll do one more. Okay, so this one here, we're going to x squared for x is greater or equal to 0. So that's quadratic. So I'm going to look at my parent function of x squared and know some of those rules off that, some of those points. So if x is greater or equal to 0, I know 0 is my first point I'm going to start with. So on x squared, 0, 0 is that point. Now I'm going to only try numbers to the right of 0. I'm only interested in 1, 1, 2, 4, 3, 9, and, oh, try to smooth curve that. And that is that top one. Now for 5, when x is less than 0. So if x is less than 0, I'm still going to go to x being 0. That's going to be my first one. I'm going to go to 5 and put an open dot. And now less than 0, it's always 5, less than 0. So it's horizontal or constant line that direction. Okay. The number one error that I get with people doing this particular problem here, come over here to the side and do it, is the confusion on what we do right. So we usually get that right. And then when we get down to doing this one, they say, oh, well, x is less than 0, so the first number that is less than 0, which is incorrect, but they think whole numbers all the time. They think -1. So they go to -1, go up to 5, put an open dot there, which should be a closed dot in reality. But we do that, and you can see then the discrepancy between what we've got going on right there in yellow, which is the true result, this true solution, and what we've got going on right there. You see how over here, nothing got graphed. Okay, we've actually lost an infinite number of solutions to this inequality, or this piecewise. Okay, so we need to make sure we do that. We need to pay attention to these endpoints and use those endpoints all the time, and then decipher whether it should be an open circle or a closed circle.